In this video, we're going to take a look at solving one variable inequalities. We're going to take this function in example 1, f of x is equal to the quantity x plus 3 times the quantity x squared plus 1 times x minus 4 quantity squared, and figure out where the function is greater than 0 and where the function is less than 0. What this means is we're going to be looking for values of x that make f of x positive and values of x that make f of x negative. All right, so what do we know about this function? Well, we know that it's going to have an x-intercept at -3, and it's actually going to be an intercept, so it's going to slice through. We also know that it's going to have a bounce point at x equals 4, and it's a bounce because of the multiplicity too, even multiplicity. X squared plus 1, if we were to set that equal to 0, we would get x is equal to plus or minus the square root of -1. And that, of course, is going to be non-real, so that doesn't affect our picture. All right, so I'm going to make a sketch now. So we cross through at -3, and we have a bounce at 4. So we cross through at -3, and we bounce at 4. Now, there's nothing that leads me to believe that this wouldn't be ending in a positive fashion. X times x squared times x, that would give me a grand total of actually f of x is equal to x to the 5th. What I forgot was I have 1, 2, 3, 4, 5 x's here because of that multiplicity too. So x to the 5th means that I have a positive leading coefficient. I have no reason to believe otherwise. And it also means that I have opposite end behavior. So to the far left, we're decreasing, and to the far right, we're increasing. So now I know something weird is probably going to happen up here that will come out of that fact that we have two non-real zeros. The x equals positive square root -1 and negative square root -1. So here we go. All right, well, what I know for sure is that my values of x are negative from -infinity to -3, and my values of x are positive from -3 to 4, and then again from 4 to infinity as we head toward positive infinity in this direction. So we're positive in 2 areas and negative in 1 area. So to answer the question, f of x is less than 0 when? Well, f of x is less than 0 from -infinity to -3. Now I'm going to use a bracket because of this symbol. If it were, or I'm going to use a parenthesis, not a bracket, because of this symbol. If it were underlined, then I would use a bracket. Now, where is f of x equal to 0? F of x is equal to 0 at x equals -3 and x is equal to 4. And then, where is f of x greater than 0? So f of x is greater than 0 from -3 to 4, and then again from 4 to infinity. So I'm going to join those two intervals together because that's a solution set. All of the numbers in those two intervals will satisfy where f of x is greater than 0. Now in example 2, as you can see, it hasn't been given as a linear factorization or even a factorization of any sort. So what we need to do is we need to find all of those linear factors. So first thing I'm kind of thinking about is what are my possible rational zeros? I'm going to pick 1 or 2, like how about 2? Let's see if I can end up with a remainder of 0. So here's my synthetic division. 24 and 2 are both divisible by 2, so I don't know, I'm just feeling lucky with 2. -16, -32, nope. What if I were to try -2? 2, -7, -10, and 24. Drop the 2. That gives me 22, and that would give me 12, and that gives me -24. Yes, hallelujah, woohoo! So x is equal to 2 is indeed one of my zeros. Now I'm left with a depressed polynomial, 2x squared minus 11x plus 12. And I'm feeling lucky about factoring this, just old school. 24x squared and -11x. Yep, -8x and -3x are two numbers that would multiply to 24x squared, add up to -11x. and then I drop the first and the last. I factor by grouping. I'm left with x minus 4 in the first group, and sure enough, x minus 4 in the second group. So in factored form, x minus 4 and 2x minus 3. Okay, so all of this work was preliminary work to get this function into a different form. I can write this as x plus 2, x minus 4, and then 2x minus 3. And I want to know where this polynomial will be greater than 0. Where will it be greater than 0? So again, here and here and here are where I got those zeros. So now I want to know where f of x is greater than 0. So I'm going to take a look at the zeros. So let's see, my zeros are at -2, 4, and then 3 over 2, which is the same as 1.5, making a really rough sketch drawn to no sort of scale. All of these show up in odd multiplicity, so they're all going to be intercepts. None of these are bounce points. And I believe that I'm going to be heading off towards positive infinity because my leading coefficient was positive. So something like this is a rough sketch. So remember what the question is asking for. The question is asking for, where is the function greater than 0? The function is above the x-axis in these two intervals. And of course, this interval is heading off towards positive infinity. So I would say that the function is positive in the interval from -2 to 1.5, along with the interval from 4 to infinity. And that is my final answer. All right, turn the page over. Let's take a look at example 3. So this one's kind of cool because now we need to consider a domain restriction. So kind of the first thing I'm going to think about is this x plus 1. Now remember, this must be greater than or equal to 0. Well, actually, let me take that back. X plus 1 has to be greater than or equal to 0 because I can't take the square root of a negative number. I cannot take the square root of a negative number. So x minus 1, or I'm sorry, let's say that again. X is equal to, x has to be greater than or equal to -1. Yeah, that's what I'm trying to say. X has to be greater than or equal to -1. I was overthinking that. As far as x minus 3 is concerned, x minus 3 gives me an intercept at x is equal to 3. I'm trying to answer the question, where is the function less than or equal to 0? I don't know, can that happen? I had that domain restriction with the square root. So to take all of the guesswork out of it, to like eliminate your need to think on your own, make yourself a sign chart here, make yourself a little number line graph. So right off the bat, I determined that x had to be greater than or equal to -1. So that is the graph of x is greater than or equal to -1. And then I also know that x equals 3 is going to be a 0 or an intercept, something like that. Well, I don't really know, I don't know what's going on here. I don't even know what this picture looks like, but I know that I have 3 key intervals. So I have 3 intervals to consider. So I don't know, like I said, I don't know what this graph is going to look like. I just know that I have 3 areas that need to be really considered, from -infinity to -1, from -1 to -3, and then from 3 to positive infinity. I shouldn't put a bracket around -infinity. Whoopsie. Okay. So what I'm going to do next is then I'm going to create some test values. So I'm just going to come up with some test values. TV stands for test value. -5, a test value here would be 0. 0 is easy to plug in. It's between -1 and 3. And then in this interval, how about if we test 10? All right. Now actually, I'm not going to test that interval because remember, I'm kind of locked into this area where x has to be greater than or equal to -1 because of that domain restriction in that square root. All right, then if I plug in 0, I end up with 0 minus 3 times the square root of 1. That's -3 times 1, which is -3, meaning that values in this interval are going to be negative. When I plug in 10, I have 10 minus 3 times the square root of 11, 7 times the square root of 11. These values will definitely be positive. In that interval, anything that I plug in is going to be positive. So I'm ready to answer the question. Where is the function less than or equal to 0? Well, from -1 to 3. And that's my final answer. All right, we're going to stop there. There was a story problem here about making boxes, and we're going to go ahead and start with that tomorrow. If you'd like to take a look at it, you might consider the following information as true. We need the volume to be greater than or equal to 600. We know that each of these corners that are cut out are x's. And this started out as being a 20 by 25 piece of cardboard. And so now our dimensions are actually 20 minus 2x by 25 minus 2x. What's a good expression for the volume then? Well, length times width times height. And in our case, the volume would be x is the height. Well, so you have a good good example to refer back to. 25 minus 2x times 20 minus 2x times x. Now, what do we know? We know that this has to be larger than or equal to 600 cubic inches. So, can you solve that? Can you solve it? What values will make your intervals? And then remember, you're looking for where is the function greater than or equal to 0, technically. Greater than or equal to 600, I guess. I don't know. We'll take a look at that tomorrow.